How does a stealth aircraft fly without being seen by radar? In the world of modern military aviation, stealth aircraft represent a technological revolution that has reshaped the rules of aerial warfare. These aircraft are capable of flying through enemy airspace without being detected by advanced radar systems, granting them an enormous strategic advantage. But how does this actually happen? In this comprehensive article, we explore the principles of stealth technology, its historical development, and the latest aircraft and advancements up to early 2026, with a strong focus on the scientific and technical aspects. How radar works. The foundation stealth is built upon radar systems operate on a simple principle: transmitting electromagnetic waves, usually in the microwave range, and receiving the echoes reflected from objects. The stronger the reflection, the easier the object is to detect. This reflection strength is measured by the radar cross-section, RCS, which represents how large an object appears to radar. In conventional aircraft, radar waves reflect strongly due to curved surfaces, right angles, and exposed engines. Stealth aircraft, however, reduce their RCS to extremely low levels, sometimes comparable to a small bird or even a golf ball, making them effectively invisible to most radars of stealth technology. Stealth technology relies on two main strategies: scattering radar waves and absorbing them. 1. Stealth shaping geometric design. The aircraft S-body is designed with flat surfaces and sharp angles to scatter radar waves away from the radar source. Key design features include avoiding right angles 90 degrees that reflect waves directly back to radar, using slanted and aligned surfaces to redirect reflections away from detection hiding engines and weapons inside the fuselage. The F-117 Nighthawk was the first practical example, with its distinctive faceted, diamond-like design that dispersed radar waves in multiple directions.
Radar-absorbent materials RAM. Stealth aircraft are coated with special materials that absorb radar waves and convert them into small amounts of heat. Modern developments include lightweight carbon-based RAM metamaterials that precisely control electromagnetic waves, new coatings that are more durable, weather-resistant, and easier to maintain. In 2025, companies such as Lockheed Martin introduced new coatings for the F-35 that improved absorption across a wide range of radar frequencies. 3. Reduction of other signatures. Stealth is not limited to radar invisibility, infrared, thermal. Signature. Engine exhaust is hidden and mixed with cooler air. Acoustic signature. Quieter engine designs. Visual signature. Specialized camouflage coatings.
Historical and modern examples of stealth aircraft. F-117, Nighthawk first generation, the first operational stealth aircraft, 1983 to 2008. Famously used in the Gulf War to strike heavily defended targets without early detection. B-2 Spirit second generation, a strategic bomber with a flying wing design and extremely low RCS, capable of carrying nuclear weapons. F-22 Raptor and F-35 Lightning to fifth generation F-22 Raptor, considered the most advanced stealth air superiority fighter, combining stealth, supercruise, and extreme maneuverability. F-35 Lightning II, a multi-role fighter used by dozens of countries. In 2025, it received upgrades to its stealth coatings and optional unmanned operation
Military
capabilities.
Intelligence Report. Stealth aircraft and radar evasion mechanisms in modern aerial battlefields. Air superiority is a decisive factor in both offensive and defensive operations. Stealth platforms enable penetration of heavily defended, anti-access, area denial, A2AD zones without early warning, allowing effective execution of CDD missions, suppression, destruction of enemy air defenses. This report provides a detailed analysis of radar evasion mechanisms, incorporating the latest available data as of January 2026. 1. Radar operating principles and the primary weakness. Enemy radar systems transmit electromagnetic pulses in RF frequency bands commonly. The X-band, 8 to 12 GHz, for high-resolution radars. Distance and speed are calculated from echo return time. The amount of reflected energy defines the radar cross-section, RCS, measured in square meters. Conventional fighter, for example F-15, RCS between 5 to 25 mem. Advanced stealth aircraft, for example B-21, RCS below 0.01 square meters. Comparable to a small bird. Strategic objective: reduce RCS to a level where detection occurs beyond the effective engagement range, allowing weapon release without warning.
2. The three pillars of stealth technology are low observable shaping. Slanted surfaces and sharp edges scatter radar waves away from the source. Specular reflection control. Avoidance of right angles and large curved surfaces. S-shaped engine inlets and internal weapons bays to minimize strong reflections. Example: the B-21. Radar uses an advanced flying wing design with refined diamond-shaped edges to
B.
reduce side
Radar-absorbent
reflections.
materials and coatings, carbon and iron-based layers. Convert radar energy into heat. Advanced metamaterials enable negative refraction and wave manipulation. Durable RAM coatings designed for reduced maintenance, as seen in F-35 block for upgrades to 025-2026, 2026 development. Smart materials that adapt to changing radar frequencies using frequency-selective surfaces. C. Multispectral signature reduction, infrared. Flat exhaust nozzles, mix hot exhaust with cool air. Acoustic, low-noise engine technologies, advanced electronic warfare systems, for example, an ALR-94 on the F-22 for active jamming and detection. 3. Major stealth platforms, status. January 2026, United States Air Force F-22 Raptor, Premier Air Superiority Fighter, Air Chess, Sata Meter Persegi, Supercruise-capable F-35 Lightning. 2. Over 1,000 units operational. Block for upgrades include a PG-85 radar and enhanced stealth B-21 radar, entering early service in 2026. At least 2 aircraft flying, RCS lower than B-2. NGAD-F-47, Boeing, 6th generation system of systems with collaborative combat aircraft. CCA production began in 2025. First flight expected in 2028. Major competitors, China PLAAF, J-20 Mighty Dragon, over 300 units. Low frontal RCS. Higher side aspect compared to F-22, J-35, J-35A, carrier and land-based variants approaching F-35 capabilities. Production expected to exceed 500 J-20s by late 2026. Russia VKS, Su-57 Felon, limited production approximately 30 units. New Isdeli 177 engine tested in December 2025. Higher RCS due to less optimized design. Challenges, low-frequency radars, VHF-UHF, detect large objects but with poor precision, passive and bistatic radars. Exploit civilian signals. Chinese 2026 research, intelligent surfaces converting radar energy into electricity, RES-energy, harvesting countermeasures. AI-assisted maneuvering, advanced electronic warfare, and adaptive stealth materials. Latest developments, up to 2026. B-21 Raider, the newest U.S. stealth bomber by Northrop Grumman, unveiled in 2022. First test flights began in 2023. By 2025, 2 prototypes were flying. Operational readiness is expected in 2026, featuring stealth capabilities surpassing the B-2 through advanced materials and unprecedented RCS reduction. NGAD program, F-47, the U.S. Air Force's 6th-generation fighter program. Initial production began in 2025. With first flight expected in 2028, it integrates metamaterials, artificial intelligence, and man-to-man teaming within a system of systems concept.
Future challenges and anti-stealth technologies. Despite its advances, stealth faces emerging threats: low-frequency VHF radars, quantum radar using entangled photons, passive radar systems relying on existing emissions. This drives continuous development of smarter materials and adaptive designs capable of responding dynamically to different radar frequencies.